All right, Unit 7, Lesson 3. Today we're going to be looking at slope fields, which, sneak preview, are these funky looking diagrams you may have seen before. Maybe if you looked ahead at the summative, maybe you remember it from our mock exam. These are going to seem really straightforward once we go over how they work. These are good places to score some points on the AP exam. This is a good topic. Let's talk about what a slope field is. It's a picture representation of all of the possible solutions to a differential equation. And so the differential equation is just an equation that represents the derivative of a function, right? The slope of the tangent line at a given point. And so if you can back upwards, you can go up to the original function, but here is the problem. There are an infinite number of solutions to these differential equations. Let's walk through why. If we have the derivative of y with respect to x is equal to x plus 3, the trick here, remember, is to separate these variables. So I'm going to multiply both sides by dx. What that will leave us with is dy is equal to x plus 3 dx. And really this is a 1 here, right? It's understood, and that helps us see this next part better. We take the antiderivative, because we're trying to go up. The antiderivative of 1 with respect to y is just y. The antiderivative of x plus 3 with respect to x is 1/2 x squared plus 3x plus c. Remember, we only do the 1 plus c because they would just kind of 2 plus c's are the same thing as 1 plus c. But so here's the reason, right? This plus c is the reason that there's an infinite number of solutions to this differential equation, at least until I give you that anchor point, until I tell you, sometimes it's written as an initial condition. If I don't give you an initial condition, it could be any of these parabolas shifted up or down. And so here's 2 of them, right? Here's just 2 of these same parabolas with form 1/2 x squared plus 3x plus c. Notice a few things about this. Notice that at any point, if x equals -3, the slope of this function is equal to 0. And you can see that, right? The slope of this function is equal to 0 anywhere where x is equal to -3. And that should make sense, because if you plugged in -3 for x, you'd get a derivative equal to 0. And so we're going to be working in breaking down these patterns and seeing important things about them. Here's another fun one I like to notice about this one. What I notice first about this, if I was doing this multiple choice, I'd say, oh yeah, let me look and make sure that when x is -3, all of these possible slopes are 0. The other thing I would say to myself here is, ooh, there's no y. My derivative does not depend on y, so I should be able to move up and down. And notice, you could move up and down any of these columns and the slope stays exactly the same. That's because this slope does not depend on y. dy dx is x minus 3. It only depends on x. The next thing I would think about is, and we're going to go through some practice ones of this, just what happens when x goes up by 1. Every time x goes up by 1, the slope goes up by 1. So check this out. This is like whatever. This slope is -7, -6, -5, -4, -3, -2, -1. Yeah, there's the perfectly diagonal one. 0, 1, 2, 3, 4. And so you can figure out what these slope fields would be, or you can draw them on your own for any given number. And so we're going to talk a little bit more about how I think they might do this on this year's AP exam. On this one, obviously, you're not going to be able to draw one of these things. But it is a good skill, and Delta Math has a good one where you can practice it. So I do want you to practice it just to make sure we understand how slope fields work. So let's say we have a slope field here. It depends on both x and y. So I'll just pick a random point and show you one way to do this. So let's pick this one here. This is the point -1, 1. And so the notation I would show here is I would say dy dx at, and I would put this little point here, -1, 3. Well, if we plug in -1 and 3, we'd have -1 minus 3. We'd have -4. And so I draw a really steep slope here at -4. So you could go and you could fill up a whole notebook, right, writing all of these different ones out. But it's helpful to try and think about some patterns here. And the pattern that I see first, when I see something like this, I say, ooh, if x equals y, then this slope should be equal to 0. And so I'll write that as just a little note here. If x equals y, dy dx equals 0, because you'd have something minus itself. And so what that would allow me to do is to quickly knock out all of these 0 slopes. And so notice that that's really helpful a lot of the time to think in terms of 0 slopes. And then, you could take that a step further. You could say, okay, well then every time x goes up by 1, right? And also I'll do one example here. Let's do this example, this first one here. Let's say instead of -2, 2, I do -1, 2. Well, so here we'd have -1 minus 2. We'd have here -2. What am I thinking through this wrong? Oh, and sorry. So -2 is the y value. So we're going to have -1 minus -2. Okay, that was what was confusing me. And so -1 plus 2 is 1. And so this slope would be 1. And you can think about it like every time you would add to x, and I'll try and match this color pattern here. Every time you would add to x, this would have a slope of 2. So I guess I didn't do a really good job of drawing this one with a slope of 1. But then this would have, so let's say that's 1, and then 2, and then we'd keep going here. We'd have a slope of 3, and I'm going to try to draw this one really exaggerated. We'd have a slope of 4. And so we could go ahead and we could try and figure out all of these different slopes here. And so let's try and knock out like what happens now that we have, notice we have these bottom ones now. So I should just be able to run the table here on what's happening as we move up. So if we start at 0 and we're increasing y, because we're subtracting y, now this should be a -1, and then a -2, and then a -3, and then a -4, and then a -5. So getting steeper and more negative. And that checks out with what's happening up there. And so we'll have, we'll mirror this pattern, -1, -2, -3, -4. And so you can see how this one's going to work here. And you can also see, now I really see what's going on, every diagonal is going to be the same. So these will all be 1s. The ones that are along this diagonal here will all be -1s, and so on and so forth. So, if you can find patterns here, it can help your life go a lot faster. But at the end of the day, if you're not sure, and it's a problem, you definitely want to make sure you get these ones right, because they are just like free money when you see them. You can test all of those individual points. So you get the idea here. All right, let's see what some other things that they could have us do. If you are given an initial condition, this is a really silly one, but it might pop up on a multiple choice. If you're given an initial condition, you can just follow these slopes. They're basically like traffic patterns. And so if I know that my actual curve here goes through the point, right? So if I take this y, if I took this antiderivative, it would be like 1/2 x squared minus x plus c. And so it's some parabola, right? But it could be shifted up or down, and I can see the parabola shape here. I know if I start at 1, -1, you can just kind of follow these points here, right? On the AP exam, they're pretty lenient here on what this looks like. You just kind of follow the pattern as it goes. So I'll go back and I'll do another one for this. Like let's say I said we wanted to, that one's kind of tricky. They wouldn't give you that one. So let's just leave it at that. Okay, so the main thing though, and yeah, okay, I did good here. This is not a particularly long one. The main thing I expect to 100% come up on this year's AP exam, because it would be hard to test as a free response question, is they'll give you one of these graphs and they'll ask you which of the following match the differential equation. And so there's no real set procedure. It's just here are some common things to look for. Look for 0 slopes. So if I look through this graph, I do see some 0 slopes. So the first thing I notice here is that everywhere along this diagonal, which sure to me looks like the diagonal x equals y. That looks here, if x equals y, then the derivative is equal to 0. And so let's see if there are any that would fit that description here. If x equals y, then the derivative is equal to 0. Ooh, that's not x equals y. Ooh, okay, so that's what, okay. This is if x equals negative y, right? Because the x numbers are positive and the y numbers are negative. And so if x equals negative y, the derivative is 0. That's actually only going to be true for C, right? So if you could really nail that one, that's only going to be true for C, right? C is the only one here. If you plug in, for example, if you just go through, so here's another way of thinking about this. If you just plug in -2, 2, you should get out 0. Do you get 0 in A? No. -2 plus 1 is not 0. Do you get 0 for -2 squared? Nope. Do you get it for -2 divided by -2? Nope. Natural log of -2? Nope. And so, don't be intimidated by like having to come up with the exact pattern. You can try points that can really help you out. That can help you out here. There's little things. There's other things I would notice about this. I would notice as x increases, the slope increases, right? So it goes from negative to 0 to positive. So I want something where when x goes up, the slope goes up. And like E, x isn't even involved. So that can't be true. And then I'd also want something, so there's always multiple ways to do it. I'd want something that when y goes up, these slopes are going from negative to positive again. I would also want when y goes up, the slope goes up. Well, A and B don't depend on y. And D, when y goes up, the slope would go down. So C is the only answer, multiple ways to look at it. Let's see one more here.